Good afternoon. My name is Victor Espinosa, student of the PhD program in Public Policy at Tecnológico de Monterrey. And today I will speak about resilience and robustness in critical infrastructure. The main idea of my research it is to bring together the concepts of resilience and robustness to be applied in the management and decision making that exists around the critical infrastructure. In this presentation, first, I will define critical infrastructures. Then, I will introduce the concept of resilience and robustness applied to these critical infrastructures. Then, I will mention some elements of the Mexican health system that characterize it as a critical infrastructure, and also I will talk about the COVID-19 pandemic as a stress for the health system. Finally, I will talk about a little bit about the Mexican epidemiological model that we are working on. Also, how we will perform the RDM analysis. To begin with it is necessary to define the concept of critical infrastructure, which is a network of independent, large-scale, man-made systems set of hard and soft structures that functions collaboratively and synergistically to produce a continuous flow of essential goods and services. With this in mind, there are several types of critical infrastructures, such as energy, financial, food, transportation, communication, water, and health, to mention just a few of them. As I mentioned, critical infrastructure it is a network made of several elements. The idea of this research it is to find which elements help critical infrastructure to increase their robustness, reducing their vulnerability, and which elements improve the response capacity of critical infrastructures, that is, increasing their resilience. The Mexican health system is conformed by a large number of elements. In this presentation, I will only mention 5 relevant elements: hospital beds, computer tomography scanners, magnetic resonance imaging units, practicing doctors, and health expenditure as a share of GDP. As you can see, the elements that come from the Mexican health system occupy the last positions within the member countries of the Organization for Economic Cooperation and Development. This is an important indicator of the current situation of the Mexican health system. Mexico's hospital beds per 1,000 populations are far below the average for OECD countries. In fact, if we compare with countries such as Korea or Japan, which have approximately 13 beds per 1,000 population, we see that the difference is very wide with Mexico, which has only 1 bed per 1,000 population. The same situations occur with the number of computer tomography scanners and magnetic resonance imaging units, since in Mexico we only have the 20% of the units that the average OECD country has. In the case of doctors, the situation is not the most positive, but we are not so far below the average for OECD countries. In any case, if we compare with countries such as Greece or Austria, we can see that we only have 30% of the doctors who practice medicine in those countries. To conclude with the elements that come from the Mexican health system, obviously it is relevant to consider the health expenditure as a share of GDP, since this element affects the other elements that we mentioned previously. As we can see, Mexico is among the countries with the lowest percentage of GDP spending on health, since only 5.5% of the budget is allocated, while the average for OECD countries is around 9%. And the difference is even greater if we compare it with countries like the United States or Switzerland. Considering that the Mexican health system is a critical infrastructure of relevance to the country, the following research questions emerge. What elements of the Mexican health system increase robustness? What elements of the Mexican health system increase resilience? And what elements of the Mexican health system have the most impact on its robustness and resilience? I already mentioned that a critical infrastructure is composed of different elements in the form of a network. And on these elements will depend its increase in robustness and resilience. But what happens when this critical infrastructure is exposed to a new problem, the COVID-19 for example? If the elements are not capable of providing robustness and resilience to the critical infrastructure, the new problem will most likely lead us to its collapse. This is why it's so important to establish which elements of the Mexican health system should be analyzed in order to determine which one makes this critical infrastructure robust and resilient in the face of COVID-19 pandemic. The idea of this analysis is that it can be extrapolated to other critical infrastructure, no matter if they are composed of different elements and under other problems. Among the main elements of this critical infrastructure to analyze the impact for the COVID-19 pandemic, there are testing, contact tracing, hospital beds, to name a few relevant ones. One way to assess how governments have acted is through data. This is why the Stringency Index developed by the University of Oxford is very useful, since it collects information on the measures that the governments of each country have taken from the beginning of the pandemic to the present day. This is done through the inclusion of indicators of two types. The first type of indicators are those that include the containment and closure policies, and the second type is those that includes the health system policies. As we can see, the national measures applied by Mexico, the United States, and China, beginning in March and continuing to this date, are not very different from each other. This index provides us with more elements for analysis and a better understanding of COVID-19 infections in Mexico. Speaking of contagion, COVID-19's epidemiological model specific to Mexico, it is an essential tool for working on answering our research questions. Here we can see a simplified causal loop diagram of the epidemiological model developed, where we can clearly see the cycles of contagion, depletion, and recovery. The epidemiological model that I am considering as a part of this work was developed at the Tecnológico de Monterrey by Dr. Mundo Molina using our programming libraries. The behavior that can be represented in the different variables estimated in the model depends on the parameters that provided and the combination of them. This is why having a calibration based on the official data published by the Mexican government is of great importance, since with this it's possible to be sure that the model reflects in a good way the reality of the infections and deaths caused by the COVID-19 pandemic. In this case, I present the deaths of the three most relevant states within Mexico, considering that there are important population centers in them. The orange lines show the calibration values of the model, while the blue lines represent the historical deaths. In general, we can see that it's a good fit, but definitely with a greater amount of information, the conditions of the model can be refined. Once we have the baseline of the model, several policies will be added. The following 5 are the main ones: social distancing, isolation, use of masks, vaccines, and increase in available hospital beds. Each of these policies will be considered within the model after a bibliographic review of the literature that allowed us to know how much they affect the variables of the established model. With all of this, we already have elements to establish our problems in a more appropriate way, grouping all the aspects that we will be explored in the analysis in a 2x2 matrix. We start with the performance metrics that we are of interest for our analysis. In this case, there are 2 relevant metrics. That's an economic cost of containment, and a third that it's actually an objective, that is flattening the COVID-19 curve. Afterwards, we have to consider all the uncertain factors that we are going to face, which can be summarized in most of the parameters that are directly indicated in the performance metrics, which in this case are contact tracing, probability of contact with infected person, contacts between infected and uninfected people, infection rate, hospitalization rate, mortality rate. The next category considers the policy levers that we might consider to be under our control. In this case, the 5 I mentioned previously, which can be considered one by one, a mixture of them, or only some of them for analysis. Finally, we must consider the existing relationships between all the aspects we have considered in our matrix. For this purpose, the Mexican Epidemiological Model of COVID-19 and Government Response Stringency Index we will work. The idea is that this section will represent cause and effect. In other words, which policies under condition of uncertainty will produce the performance metrics that we are expecting. One of the initial findings could land in the prognosis of the date of stabilization of cases. This happens at the time when the infection rate is equal to the recovery rate. That is, basic reproduction number is equal to 1. R0 is equal to 1. In other words, the moment when the maximum number of infections is reached with the current containment policies. In this table, we can see for different months the probability that a state will reach R0 equal to 1, considering the entire ensemble of scenarios in the experiment. The calibration we see here is from June of this year. As you can see, the situation looked encouraging for the months of December and January, but the most current calibrations have been modifying the predictions to a great extent, and now December and January are not so optimistic. In conclusion, I have to say that this work is still in progress. The main intention is that through the analysis of the Mexican health system in the face of the COVID-19 pandemic, the greatest number of relevant elements, or those that have some incidence in the functioning of the system, can be considered, as well as those that have an impact on the evolution of COVID-19 infections. And in general, if we know the elements of the system that we are analyzing and we determine which are the ones that have an important impact in the increase of the robustness and resilience of a critical infrastructure, this is an excellent way to support the decision making that allows to face the problems, no matter their size or reason, that could be presented in these systems or critical infrastructures. Thank you very much for your attention.
Thank you, Victor. Now I'm going to turn it over to the team from Georgia Tech School of Civil and Environmental Engineering. This is Katie Pope, Perna Site, Adjo Amekutsi Kennedy.
Good evening, everyone, depending on where you are. My name is Adjo Kennedy, and I'm here with Prerna Singh and Katie Pope to talk about handling deep uncertainty using DMDU methods in transportation planning. Next slide, please. So transportation planning has been required by law since 1956. It became performance-based by law in 2012. And to your right, you see the standard transportation planning approach, which starts by casting a vision and then flowing them through goals and objectives that then are propagated through the system through alternative improvement strategies that find their way into a long-range plan. The long-range plan exists for 20 years, 20 to 30 years. Now, with all the uncertainties that we are facing with climate events, changing hazards, and known unknowns, it's clear that we need to be able to handle deep uncertainty to be more effective in planning. I'm going to turn it over to Katie to talk more about what we've been doing.
Thank you, Dr. Kennedy. So I'll start off by saying that we know that there are different types and different levels of uncertainty. And many of you might be familiar with this framework already, where we have these 4 levels of uncertainty. But this framework really emphasizes the different models and outcomes that we can explore in order to actually handle the uncertainty in transportation planning. And so, for example, we know that temperature is going to increase. We just don't know by how much, which is where sensitivity analysis can come in as a method that supports planning and decision-making for extreme heat in transportation. And this would be an example of that level 1 uncertainty, where with sensitivity analysis, we can get a clear enough vision of the future. Whereas level 2 uncertainty, we have a range of possible events, like for flooding, we can explore 50, 100, 500-year flooding events and get a range of these possible futures and plan accordingly. And we have a couple of other examples, but these are the levels of uncertainty in transportation that we're facing today. And another way of visualizing the impacts of planning and decision-making on consequences can be seen here, where we've really added this 3rd dimension of planning when assessing uncertainty and consequences of an event. And what we're trying to say with these different examples and different combinations of uncertainty, planning, and consequences is that if you can effectively plan to make decisions, it could really have an impact on the extremity of consequences. And I just want to touch on one of these examples, the 2011 Great Tohoku earthquake in Tokyo, because the event itself was a higher level of uncertainty with that magnitude of an earthquake, but planning and decision making was also at a high level, and so consequences of that event relative to the worst possible consequences that could have happened in such a high magnitude earthquake were low. Whereas on the contrary, we're facing COVID-19 right now in the United States, and the uncertainties are high, planning a little bit lower, and we're still realizing those consequences today. So finding ways to effectively plan and make decisions can have a huge impact on those consequences that we face. And so our research group has been exploring these decision-making under deep uncertainty methods and how they can really help transportation decision makers plan effectively and cost efficiently for some of those deeply uncertain events that touched on in the previous slide, as well as future events that we're not sure about. And so we've been doing that by exploring the evolution of these methods, strengths and limitations in a transportation context, as well as applications to transportation, and the possibilities of integrating DMDU methods into traditional transportation frameworks that Dr. Kennedy touched on earlier. And we're going to need all of these methods of planning for deep uncertainty because even today we're facing COVID-19, but in a transportation lens, public transportation has been suffering from this event because of a drastic decrease in ridership and the need to plan for post-pandemic recovery, which has a lot of deep uncertainty. And so building off this example in public transportation, the New York Metropolitan Transportation Authority has warned of this event of COVID-19 as a doomsday event for public transportation. And there are a lot of uncertainties around how public transportation is going to recover from COVID-19, not just funding, but also ridership levels, modal shifts if people are going back to their vehicles, and also work from home trends, and if there are cost reduction measures, which ones are the right ones to take. Which brings us to our applications of DMDU methods to transportation planning. And we're gonna build off of this public transportation example just because it's something that is very relevant to this year in 2020 because of the pandemic. But we went through and examined a lot of the methods presented in decision-making under deep uncertainty from theory to practice and found specific applications that are applicable to public transit, including robust decision-making, which can be used in transit to help decision-making a plan that satisfies different objectives of something like reliability, on-time performance, or expansion of services. And we also have infographic decision theory where both robustness and opportuneness are explored. A more opportune future for transportation could be a future of adequate funding and more federal funding support, which would allow for continued expansion of services. And then we have a dynamic adaptive planning where monitoring systems can be put in place for different parameters like technical performance, costs, revenues, ridership, which really allows for an initial transportation recovery plan to be changed as we learn new information. Then we have dynamic adaptive policy pathways, which also emphasizes that monitoring approach, but really focuses on the timing of certain actions. And so if we see a future where ridership doesn't return to a certain level by a certain time, then decision makers can make that transition or shift to a different plan and adapt different actions to address ridership or different cost reduction measures for that specific agency. Then we have engineering options analysis, which really dives deep into the technical performance of something like a bus or a subway system and how that performs in different futures. So as we explore these DMDU methods, what we've really come to realize is that there are several key attributes for handling this deep level 4 uncertainty in transportation planning. The first attribute is that planning must really be dynamic because of such rapid changes across many aspects of transportation. For example, here, innovation in autonomous vehicle technologies. In addition, planning has to be adaptive because we have to plan for deep uncertainties in future climate conditions or population growth or other major changes that could affect transportation. And in order to plan for deep uncertainty, planning must also be open-ended and flexible so that we can really incorporate new knowledge as it's learned and enhance our thinking and planning processes over time. Planning must also be complementary to existing transportation approaches and should be able to handle multi-agency input so we can integrate the objectives and expertise into successful transportation planning for deep uncertainty. And with that, I'd like to thank you all for your time, and Dr. Kennedy, Prenna, and I can answer any questions that you might have.
Thank you very much, Katie. With that, we now move on to the presentation by Vivian Liu, Amideep Gupta, David Gold, Patrick Reed, and Lindsay Anderson from the University of Cornell. Whenever you're ready, Vivian, please share your screen.
Okay, thank you, Edmondo. Hey everyone, I'm Vivian. I'm a PhD student at Cornell University. And today I'm gonna talk about the transitioning power generation to distributed and operationally robust microgrids. The motivation behind this project is really to just take into more objectives into consideration for the power system planning. And one major driven factor behind it is to reduce the greenhouse gas emission through the power systems so that we could slow down the climate change process. And as you can see in this figure, there's a crazily increase of CO2 emission over the past few decades. So different regions across the world has the plan to realize carbon neutral in the next 20-ish years. For example, in New York State, we have passed this act, so it's enforced by law now to achieve 70% renewable energy by 2030. And just for the record, we're about 30-ish% right now. So we have a long way to go, and we have a lot of wind, distributed solar, and storage units planned along the way. Just to quickly introduce what is a power system. So a power system consists of 3 subsystems. We have some centralized generation that's powered by either natural gas or fossil fuel, so they're not that clean. And then we'll bring up the energy to, bring up the voltage and pass the energy through the transmission line. And then we'll decrease the voltage and further distribute the energy to different consumers. We'll be focusing on the distribution system today because the solar, especially, you might have seen them on the top of your roof or your neighbor's roof. So it's like distributed. And also the storage unit and solar could, there could be a small wind turbine near you. So they're more likely to come into the distribution system, which will bring a lot of uncertainty to the system. And this will actually give us a microgrid. So the difference between a microgrid and a distribution system is that we now have some local generators, storage unit, and we're hoping to engage some of the users to provide some flexibility from the demand side. All of these are really to compensate for the uncertainties brought by the renewables, because we're going to have a lot of them. And finally, one last characteristic of the microgrid is that it's not only buying energy from the utility grid anymore. When it has some extra, it can actually sell it back to the utility grid. So the things we can control are the things indicated by the red boxes. The question we want to answer now is, how should we come up with, the control strategies for the things in the red box under the deep uncertainty brought by the renewables? And through these control strategies, the goal we want to achieve traditionally are maximize the expected revenue. but we now we care about the environment more, so we also want to minimize the greenhouse gas impact. And microgrid, just as its name, is just a tiny version of the power system we had before, so it's more vulnerable to the uncertainties. We want to maintain high enough reliability. And lastly, we have this goal to smooth the curve. This is a very famous stack curve of California. This is their demand curve, because like in the middle of the day, they will have a lot of solar coming in, and which will drive the curve down. But when the sun sets, the curve will just bump up, which will cause some problem to the generator ramping condition. So we have 4 objectives now, which represents different stakeholders, and they're competing, or it's really hard to tell their relationship actually. So this is really a multi-objective optimization problem to be solved. So come back to our control strategies. We chose the radial basis function to model our control strategies. And the reason is because the radial based function, for each of them, it has 3 parameters to fit. And after we add several of them up together, we could derive this nonlinear, non-convex, and multi-mode curve, which will be which has this very similar characteristic of like the expected either generation or battery control curve that we want to derive. So the next step we want to do is to find the information that could be, the most informative and could improve the performance for the policy curve we want to fit. And here are some candidate information. For example, we have the battery level, which is part of the system state. And we have forecast of the wind energy, solar energy, and also the demand from the customers. There's just a huge amount of uncertainty there. Just to put all this together, we adapted the evolutionary multi-objective direct policy search framework from the hydrological field. It's essentially a simulation framework where, just to fill in each part, we have a simulation model for our microgrid dynamic. We'll be playing with these ensembles of predictions in a little bit, but after the simulation take in these inputs, after the simulation, we get the metrics or the objectives of the goals that we care about, and we'll pass them to the Borg algorithm, which is one of the best existing MOEA algorithm to optimize the parameters we want to train for our policies. Let's look at the input for a little bit. So we'll try several different combinations of the inputs. We'll start with only the battery state, which is the system state, and there's no prediction at all. We'll slowly add things up until we have like every possible prediction we could gain. And in the end, we have the perfect information policy, which is where we assume that we know exactly what will happen for the next day. And the reason I say next day is because the power system, the electricity market, they clear every 24 hours. So we usually want to plan for the next day. And the perfect information policy is derived by the dynamic programming. So that's like the Oracle performance we could get. And what I'm showing here on the right are the Pareto Frontiers for different cases. And as you can see, some of the objectives are competing, and the relationships are very complex for some of the objectives. And this is something a priori approach cannot give us. That's why we chose this a posteriori approach to tackle this problem. And let's take a closer look at the most competitive 2 objectives. where we want to maximize the revenue and minimize the emission. So the bottom right corner is the direction we want to go. And as we can see, the yellow dots that indicates the perfect information has the best Pareto frontier, and the purple dots where we don't have any prediction information at all performs the worst. And all the other things in between, like different combinations of the predictions, is sort of narrowing the gap between the basic and the perfect. So the next thing we want to do is we drew this line. So we want to compare the policies along this line where they have very similar emission level, but the revenue is very different. And so for the parameterized policies like the radial basis function or the neural network, one problem is that we suddenly lose the ability to interpret what's going on with the policies. So next, we want to compare these policies and we want to open the black box and see how the different combinations of information are being used. We'll use the tool which is called the time varying sensitivity analysis. Essentially, we take the derivative of our RBF policy and we calculate the variance with respect to each piece of information and the covariance of each pair of information. And what they give us is the first order effect will tell us how each piece of information is impacting or is explaining our final decision, the policies. And the second order term will tell us how each pair of information are co-impacting the performance. Here, I just plotted out, along that line, we have 6 policies, 6 cases, and we want to compare them. This is for the generation. So for each hour, how much I should generate. And the thick black line is the perfect information case. That's the best possible performance. That's something we hope that with some of the predictions we could mimic. The purple line here, which contains like all the available prediction information, sort of gave us the most similar results. So on the right, I plotted out the time varying sensitivity analysis, where on the x-axis we have each hour of the day, and on the y-axis it indicates the portion of variance that explained by each piece of information. So for example, like for the first 7-8 hours of the day, the predicted load is driven the performance. But in the middle of the day, the solar and some interactions are impacting the results. And that's why we see this deep drop, like in the middle of the day of the generation, dropped very comfortably, and it knows that it can ramp up later. Just very quickly for another case, just to show that for the battery control, it's a totally different story, where we can see the combination of informations and like when the information are being used are very different here. Maybe we can talk about this offline if you're interested. And finally, we want to do a robust analysis over some deep uncertain parameters. So here's a bunch of them, and we generated 1,000 different states of the world across these 5 parameters using the Larton hypercube sampling. And we want to use the factor map to help us know, like, under what combination of the scenarios could we maintain the similar level of the performance of the objectives, for example, for the revenue or reliability. And just to finish my story, where we have more solar or wind coming in, let's look at the red figure, where we have more solar coming in, and we start to see these gray dots indicating that we cannot maintain the reliability level anymore. However, if we could expand our energy exchange limit a little bit, we could comfortably stay reliable. And that also means we could more flexibly exchange or buy or sell energy with the utility grid. Just very quickly, some conclusion. So this EMO DPS framework helped us just move projects our problem into a much higher dimension, where we saw like how complex of the relationship between the stakeholders could be, and the time varying sensitivity analysis helped us open the black box of how the policies that we trained are working, and more importantly, like when the information are being used and how they're being used. And lastly, the scenario discovery tool really helped us to have a sense of what if some of the deep uncertain parameters that we cannot agree upon in the beginning when we set up our simulation changed, like the wind and solar. We sort of know they're coming in, but it's hard to know like the impact from them. Is our current system ready for that? And the scenario discovery really helped us identify like which other elements from the system could be changed to accommodate these renewables and their uncertainties. With that, I want to thank you very much for your attention, and I would like to take any questions or comments. Thank you very much.
Thank you very much, Vivian. All right, so let's open up for questions. If you have a questions, you can raise your hand virtually, or you can write it on the chat, or you can also unmute yourself, and then I will direct your question to the speaker. So I see one question already here in the chat from Pera Pan. So Victor, one of the policies that you pick, face mask, has contested opinion and unclear effects on how it can prevent COVID-19. How do you deal with this contested and unclear effects in your project? Thank you.
The use of mask, it is important to mention that everything that I am considering in my research is based on a very strict systematic review of the literature. So if I'm going to put some elements of the mask, for example, and I'm considering this in this case, I'm going to base the number or the element that I'm modeling in the epidemiological model in a way that I have to respect the things that other authors investigate and other researchers do about the use of masks. I have a little, well, not a little, a lot of papers that use face masks like a really good way to prevent, not avoid the COVID-19, but yes, to reduce the infection. So that's why.
Right. Thank you very much, Victor. I'll ask a question to Katie. Katie, you do this comparison, between frameworks, and then analyze their potential applicability to transportation. How different are the frameworks in terms of the potential framing of the problem? Did you find substantial differences in how the different DMDU approaches could actually be used to frame the problem?
I'd also like to invite Dr. Kennedy and Prenna to answer this question as well, since we worked on this as a team. But more recent literature has shown that there are a lot of possibilities for joint approaches. And so robust decision making, for example, could be used with dynamic adaptive planning, dynamic adaptive policy pathways. And so we are exploring the use of a combination of approaches from implementations and applications in literature. They are different, but many of them have similar aspects, like based on satisficing or really encouraging the implementation of a monitoring system. And so we're still in that review process and exploring how they can be applied to transportation. But if Dr. Kennedy and Prenna want to add anything to that, that'd be great.
Okay, so
I'm also looking at Vincent's question in the chat, which is saying that how do we get planners doing all these? So I'll add that and answer. So we have two sort of project contexts in which we are doing these explorations. We have a small bets project, which is purely exploratory, that we got from Georgia Tech. And so we're looking at black box or black swan events. And the research question there is, how do you plan effectively for transportation systems when you have no idea about the major hazard? And then we have a more practical project context, which is from the Georgia Department of Transportation, where the main research question there is, how do you transform into an agency that is resilient in an efficient manner, in the most efficient manner, and continue to address hazards adaptively. So we have started the approach looking for the practical context, looking at a capability maturity model around resilience, different resilience dimensions. And the intent there is to understand where the agency sits and begin to look at different pathways to move the agency to the next level. That is the place where we intend to put together a number of DMDU approaches. So in answer to your question, Edmondo, we are not absolutely certain yet which methods we will use, but we've started looking at the fundamental attributes and how those support the areas of uncertainty where the factors are strongest in affecting the strategic goals of the agency. Okay, so that's the general idea for now. And it's evolving as we move forward. In terms of the question, how do we get planners to do this? I think it's very encouraging that the Georgia Department of Transportation has actually funded this work. And so I think the thinking is evolving forward, that we do have to think about resilience because it does affect system performance. And currently we are operating in a performance-based framework in transportation planning. This has been the requirement by law since 2012. I hope that answers the questions.
Thank you very much. Thank you very much, Dr. Kennedy. All right, so we have other questions here in the chat. Let me see, building on the previous questions to Victor now, Jonathan Lamontagne is basically asking about how did you use social distancing in the model, and if you deal or not with the fact that this policy response can degrade over time.
The epidemiological model that we are considering has a variable of social distancing, not as a policy, but yes, as a policy. It's like a state zero, or just to say. But also we are modeling the policies that I mentioned, and we are considering a calibration, a weekly calibration to the info that we have with data of mobility. So that's why we can put all the calibration on the information that we are using. That if we are using maybe a very large value of the policies, or maybe we can adjust that value that we are considering in the model.
Thank you very much, Victor. All right, so I have other questions here. Let me just ask a question to Vivian. Vivian, how do you say, what is the product of a control strategy under deep uncertainty? Is an adaptive plan? It is a functional, policy. And then basically the analysis that you presented here today tells you which pieces of information are more valuable for that, functional policy form. What is actually, how do you translate that into, the MDU context?
Yeah, sure. So the policies we're constructing are like adaptive to the external informations, and those external information actually like have, I would say, two layers of uncertainty there. The first layer, which maybe is the like uncertainty people talk about in the weathers, in wind, in solar. And then there's another level of deep uncertainty where we just don't know for now how much of the wind or solar will be along the time. So it might be that next year we have, or just because it's just so distributed, especially for solar, maybe one customer would install a solar panel on top of their roof. And that means not only like the uncertainty in the solar itself is changing, but also the scale or the capacity of the energy are also changing. So we sort of want to capture that with the policies we're deriving and taking that into consideration of our system control.
Thank you, Vivian. I have another question here from Ben Rakunok, and it's for Victor. How do you plan to define resilience different from robustness? What makes something resilient versus something robust?
Yeah. When we talk about robustness, we are well. I'm thinking on reducing the vulnerability to, for example, this health system to collapse by the COVID-19. When I'm talking about the resilience, is the capacity of the critical infrastructure, in this case, the health system, to respond, the response capacity that the health system have. And the difference between them, I think one is prevent and another is like some emerge. And maybe that's the principal difference that I have. Like I'm analyzing these two terms. I'm also doing a very strict literature review to strengthen this difference and the definition with the critical infrastructures.
Thank you very much, Victor. I don't know if there are any more questions from the audience. All right, if there are no more questions, I want to thank our speakers today for this wonderful session. It was a very interesting set of presentations, and I'm looking forward to hear more from you soon. Thank you everyone for attending. It was a pleasure to have you here.